This is the last lecture of the whole semester. Actually, we have done, I guess, 12 lectures, but one of them was repeat, so summary. So we have recorded 11 lectures so far. So this week we are going to cover up the whole semester in a way. The way we are going to cover up the semester will be working on sample problem cases. Today we are going to cover 3 items. The first item will be once we have this design of a problem with a data where the data itself might refer to itself and some other data types, but in return, if you have connection in between the data organization, we will see how we can reflect the interrelation between different pieces of data into the design. So that will lead us to examine how we can come up mutually recursive function designs. Secondly, we are going to look at the problem where we have higher order functions. That means the functions we are going to design might produce and consume functions. And as a third case, we will look at the design of a function where you consume 2 inputs, but both of them are determinant primary sort of inputs, because you might need to traverse both input at the same time. So that will that will lead us to examine what sort of template we need to come up when we need to examine and work on more than one primary input for a function. So let's start with the problem where we are going to look at the functions where design of the functions where they are mutually recursive. So principle is not different. We are not going to come up with a new material, but we'll see if we reflect a straightforward design recipe, which starts with problem analysis and data definition, you will end up really integrated and advanced sort of functions. So for that problem, we are going to look at an example. In this example, let's say we have a file system, very simplistic file system, just to focus on the problem. And in this file system, we have directories and files. And somehow we wanted to represent this file system in Rocket, in the student level Rocket environment. So this is the thing we are going to work on. So first we need to define the data where we are going to hold information about our files and directories, all of them as file system. Then we will see what sort of templates we need to organize. So my question is, how would you, let's assume it's your job to design data for a simple file system. We have directories and you have files, subdirectories and so on, something like that. So how would you come up with a data definition? Let's say pick and assume a less realistic data definition, but by the time on, maybe towards next semester, we'll work on more realistic data definition of a file system. But at the moment, let's say we want to somehow represent our file system, so we will be able to run some functions, like looking at listing the files under a certain directory, searching a specific file, or collecting the total usage, or looking number of lines or number of whatever you have designed in the file system. So any idea what sort of things you would do? Yeah, Burak?
We can see it as a tree.
Yeah, definitely. That looks like a tree. A file system, usually it's called directory tree. That's why it's called a tree. So that means you need to come up with a data definition for the directory structure. So for a directory, you might need to hold.
I would use list to hold the data.
Yeah, you would. Yeah. No, Eren says I would use list for, but you would use list for what?
For the whole tree.
For the whole tree.
I designed the list as in the list of a list there will be a directory. In the directory there will be files or other stuff, and in this list there will be other list which is a directory too.
Yeah, I think I got the point. Well, that's more advanced than I would lead you to end up, but we will come up with something very similar. So what he suggests is we are going to use a list. So within the list, we will contain all the information. But that means within the list, you should encode the hierarchy as well. So you should encode the hierarchy or subdirectory structure within the list as well. So that might lead you to come up more definite, concrete representation and analysis and the definition of how you organize your data in the list for this particular case. But let's take a more straightforward approach and simplistic approach. You could come up, as we have suggested in first place, with a structure for directory. So at your own data structure. For the directory, that means within that structure, what sort of information you need to hold, for instance?
Directory, that would be directory and files.
Yeah, for this one, you will use directory level, or just maybe if you are going to use a tree-like structure, that will be a node, for instance. That will be also a node. That will also be a node, but the files would act like leaves. So that means for this thing, that means that the structure you will come up with directly will be like designing for a node for a tree. But for the node, what kind of information you want to hold in the node? That's the thing you need to design. So let's start with the data definition. We want to design a structure called directory. In a way, it's a node design for a tree. So for that thing, how many fields do you think you might need to come up? I don't know, for how many number of pieces of data you want to hold within the node? So what sort of information you need for the to hold the things in a directory? Yes, someone?
You should present your parent node.
First of all, we need to come up with a representation of contents or sub-files or files or subdirectories within the tree, under that node. Other than that, you might decide to come up with an identifier to represent the node itself. For the simple case, let's say for the identifier of the node, we can use a name. I'm just making things simpler. This is one thing. So that will help you to spot the node itself. This is a simple one. So other than that, somehow we need to tell what are the things under the tree, under that subdirectory, under the directory. So how would you organize your data in that case? So would you put them all in the same place? But the thing is, you need to realize that some directories will have nothing underneath. Some directories might have just directories, some of them might have just files, or mixed up. And the number of items will be varying. So what is the natural data structure where you have varying number of items? Lists? Yeah, that means that you could use lists to hold things. That comes to your idea in first place. Because you don't know how many items you want to have, you are going to end up and it should be dynamic. You should be able to add new things or extract new things out of that. So that means you will have a list. So do you think we can have a single list or double list under that structure? So one list should be sufficient or not? Sufficient. Should be sufficient, but that means we need to be careful about about the items we are going to hold in the list. So that means, let's say, in the list, we are going to keep directories and files. So that means somehow we need to...
For files, we can define structure to hold name, size, and ownership of the file.
Whatever. So that will come to that point before finishing this up definition. So that means the name is, let's use string for the name at the moment. And the subs, we should define what subs is. Subs is list of files and directories. So that means, let's say it's list of both files and directories. So we'll need to make more clear definition of that thing. We will come to that point. But since we have said we are going to represent or need a representation for the file, now we need to consider what sort of information we are going to keep for the files. So as you have said, the things we might use to identify, like file names or file pointers, or whatever is based on what file system you have. But for the moment, we just, let's say, we use the names for identify the files. Other than that, we might have a summary information like size of the file, creation date, permissions, and blah, blah. But let's keep the file name, the size, and besides, we need to hold a data structure where we keep the content of the file. So, that means for, let's say, define our file structure, we have a file, it has a name. We decided to have size and content of the file. So now make sure how name is represented. Name, let's say again, string. Size. Size will be number, and it represents what? It represents size in, let's say, in kilobytes. In case, I mean, you could come up with a more other than that. And how about content? Content is, it can be, if it's a binary file, it will have zeros and ones inside. If it's a text file, it will have textual information. If it's an image file, again, pixel information and so on. So let's make simple file system where we don't only have text files. That means you could have Word kind of stuff. You could have your codes like and kind of things. So now let's see how are we going to hold information in the content. So if it's a text file, we can have a single string, or we can make a list of lines. So where each line itself is a string. So that's a simple and advanced. I mean,
it's a simple string because actually when we see a new line, it's actually
just another character.
Yes.
Is how it's representation. Okay, so you will have just string. Yeah. So instead, this is Eren's suggestion. Why just not use the string? Because a new line is just a character. That's definite. So now we decided to use string to represent the content. So we have these things, and what's left out here, we haven't cleared how we represent what is list of files and directories is. So we need to clarify what the list of files and directories is. Is what? So it's a list. So that means we should be able to represent no items, and we should be able to represent an organization of data in a const structure. But if you examine, for instance, that const structure, the first item is a directory. Consider, and you will put the other things in the second compartment. And for this thing, you will realize that the first item is file, because you have two different sort of items you can hold. That means you should be able to clarify what you are going to expect if you open up the first component. So how many cases you would have to represent the whole thing?
3 cases.
3 cases. One for the empty, one for when the first item is file, the second one when the first item is a directory. So it should be one of these cases. An empty and a const structure, but how would you denote that the first item is file? You would say, and the first component it's a file, or you can, well, it will be make file. That will be more proper definition to say it's make file. File is large, yeah. Make file, for instance, a name, one txt, like that one, and a size, so it's a 2K, a content, some text. So that will be a simple file representation. It's a make file, and what's the second structure? In the itself. List of files and directories. And the other option is const is a pair of directory. That means make. So let's think of a simple directory like this one, an empty case like C. It will have a name and an empty list. So, and again, you will go back to list of files and directories. So now we have represented a simplistic file system where we only hold text files and we represent text in strings. And for the directories, we just keep the name. For the files, we also hold this file size. So that's really simple, but not very unrealistic representation. So now let's come to, so maybe we can, let's instantiate this organization into our file system, so we will be able to use them for the test cases and so on. So we do have, in this case, we do have a simple directory structure. And in this directory structure, there are just 3-4 directories. So let's start with the bottom lines, bottom hierarchy. So we will say define D is what? Is a directory of, it's nothing underneath. So it's like make directory. This is the short name and it's an empty directory. Maybe we need to represent, and again C. Define C, it's again a directory structure. It's again empty, yeah. It's again empty. Maybe it's time to represent some files like 3 or 1 txt. Define F1, let's say, as a make file structure. We will have one text, yeah, txt, and then it should have that's a 2K. I'm not sure if we'll be able to, and put some contents, some text file. So that will be the one file system. And the other thing is the second file. Let's say define F2 is a make file structure. And we do have, let's say, let's say this is a record file, and that make some content inside it. So let's say we have a lambda expression. Lambda x is x. Oh, let's do some fun lambda expression. Let's make this the function, and we will have. This is how actually your compiler works. You give the text, your all code you write as a text file, and it's going to be parsed and compiled. This is how it's simply as a text. What you generate in first place is a text file. So something like that. You will come to examine such kind of parsing stuff and so on. Partly maybe next semester, where just simple things, but in advanced classes you'll be able to do lots of other job. So let's say, I don't know, x. Again, so I don't know whether it's correct or not. So this will be the another file. So we have one CB, and we can define the other 2 files, 3 and 4. Yeah, define F3 is a what? Is it again a text file? Maybe you can use this thing. So this is the text file. Is a 3. txt, let's say 6, and let's say this is the end of the semester. Yeah, so we do have another file, so we can, now the F4 is a rocket file. So let's assume that you have started to code some simulation for this thing, and you hold it there. So let's say it's again 4K, but you have started to say define with 200. That's the first global constant, but nothing left. You were sleeping, or something like that. So now we have all of our files and completed directories. We did define CNT. Now this define. Yeah, it's a B. Then for the B, we will say we are going to make a directory. It's a directory thing. So we are going to have a name for it, which is B, and a list of items underneath. In this case, we have file 3, file 4, and D. So it's like F1, F3, yeah, F3, F4, and we have defined D. So this is the thing you would have. How about if you want to define A? This is the last thing we are going to define, I guess. Is again a directory. So we construct this thing, and this is the identifier we decided, and this is the list of files and directories underneath. Is B, F1, F2, and C. So I guess we have enough examples to do so. So now let's, before doing any really function implementation, what I want to practice with you is now design templates for the functions which consume a directory, another function which consume a file, and a template for a function which consumes list of files and directories. So let's start with the simple one, which is the file, I assume. So that means we consume a file, and at the moment we don't care what it's going to produce because we are writing the template for a generic function. So let's say this is the F for file, and this is the input. What should be the template of this function? What's the template of the function now? We consume a file. So it always consumes file, nothing else. So we don't have any multiple data types. So we focus on selectors of the thing. So it's a file name of F. This is the first thing we will examine because this is one of the components. And the other than that, what we do have is a size information and the content. So let's just make them appear first. So this is the size, and we would have the content. So this is simple structure template. But now we need to examine every one single structure, if it's good enough or whether we need to consider anything else. File name is a what? Data type. It's a string. So we will be able to use it. So it should be fine that we don't need to do anything else. So it's a string. How about size? We have decided that it's a number, so we will be able to use it immediately. How about content? It looks like it's okay. We can use it as well, just here. So it's now we have done with a simple template where we do have just data extracted, ready to go. So now let's look at the data structure of the directory and design a template for it. In this case, we do have directory as the input, and probably we'll do something on that. Lots of things we can do, but the template should be the same all the time, more or less the same all the time. So we do have a file for directory in this again. So let's say this is D, and now we examine what should be the template for this one. Let's just check it again. So it's two components we do have. The first component is again a name, and the second component is so that means let's extract these components D, and the second component is, let's see what that is. They're subs. Okay. So now we need to consider the components one by one. Is string, that's fine. How about that thing? It's list of files and directories. It's not a simple thing to go with. So that means we need to indicate how are we going to deal with the data when it's a list of files and directories. It is the case where you might decide, because you don't know what are you going to do at the moment. We just come up with the template for the function. But that may be a hint for this case that tells you, well, you might need to run a helper function, like a function which deals with this. So it might be, let's say there's a function which is you might need to design to deal with this. So that should be enough for the template. And indeed, next thing we need to do is examine the template of list of files and directories, which means you will be able to use this template for whatever reason you came up with consuming a directory. So now let's hold the structure of the template we are going to use over and over again, maybe. So now let's design a function which consumes a list of files and directories. So okay. So now we have list of files and directories, and we are going to do something. So this is the function header partly, list of files and directories, and let's say we are going to consume this thing. So what's the shape of this template? It's a condition template because we might need to remember that the data definition tells us it's one of these three cases. So that means we should reflect this organization into our template. So we will have one for empty, where file starts with, and where directory starts in the list. So this is the case. This is the general shape. Now we have to identify questions. The first one is the question whether this is empty or not. So now, what's the second question? What's the second question for? So exactly, what's the exact expression for this? Whether it's a file. But we need to ask whether this thing is file or not, because this is a predicate function which is generated automatically when you do the file thing. But what is the input for this one? Are we going to write L of t? Is that correct?
No.
Because L of t, it's a const structure. It's never going to be a file. Either it's empty or const structure. But what we want to determine whether the first item in the const structure is a file or not. So that means we should extract the first item and then check whether it's a file or not. So as Gizem suggests, we are going to write the first item, whether this is a file or not. Now we have a proper question. And the other case, we need to examine whether the first item is a directory structure or not. But this is the only case left out, so you should be able to safely say this is the else case. So now for that thing so far, we have examined what the current input is. It's just one stage in the template, and the second stage, now we're going to check how are we going to extract the things inside. So if it's empty, there's nothing else left to extract. But if it is not empty, that means we have list of files and directories. It's a list, so we will consider the list selectors, which is the first component. And for the second component, we have the selector called L of t, or Kar and Kıdır in old good days, or still we can use them. Okay, so are we done for this thing? We shouldn't be done because as you might realize, we should check every single item. The first item is a file. So that's not a simple structure. That means probably it's the case where you might need to design a helper function just based on the purpose of the function when you have one. So at the moment you can indicate, well, in this case I'm going to come up with an expression, whether a separate independent function or in-place expression, where I might need to open up data in the file. But we know that there is a template we just have done which opens up the file thing. So we can think that this is the function template you might need to use. How about that one? It's again a list of files and directories. It turns back, it goes back. So that means it's a self-recursion point. So that means you will be able to use the same recursion over again. So we have this thing completed. How about, is there anything else we are left out for this thing? I think no. So how about this case where we have a directory as the first structure? This is the thing. We would have a first item. What's the first item in this case? It's a directory. That means probably you need to work on that structure separately because it's not a simple data structure. It's not string, it's not number. And we have designed a template for the directory. a function, generic for a generic function. So you might, this is the indication where you might need to use this thing. So this is the idea we will have here. And again, for the rest of the item, we should be able to go back smoothly. So that completes a generic function template, which consumes a list of files and directories. But what I want you to realize here is the relation between the templates. Basically, maybe if I make it smaller, you should be able to see it more easily. Like, now look at the three things and the organization and relation between the templates. So this is a function, a generic function. With this function, you refer to another function. But if you examine body of this function, the general structure, you see that in this case you go back. In this case, you go back to refer itself again. But in this case, in the second condition where you end up with a file, you go back to the file itself. But then it tells you that you should be able to use things directly here and done with it, whatever you need. But if you go to directory, that means you are in this function, you have a call, you go to another function, but this function tells you go back again. So now we have a mutuality between these two function design. This is nothing, we end up in straight simple mutuality, but we end up with this mutuality by following the data definition. And this is important in recursive function designs. This function might act like a self or secondary function for this body function, or you can start with that function and use this as a secondary function. So there is no one auxiliary to the other, but it's a mutuality in between these two things. So now let's look at a more concrete example. Let's say we want to run a function, or like system function. We want to design a system function which tells us what is the total characters in the files we have. We will want to give a directory as a starting root directory, as a starting point. I want to compute number of characters in entire directory. That means within the files directly under the directory and within the files under the subdirectories. So are we okay with so this is our purpose for the function implementation. So that means we want to give a directory as the input. I want to get a number which represents number of single character, or actual single strings, let's say. Not character but more single strings. It's like A will be one, B will be another thing, and so on. So this is the function we want to design. And let's clarify the contract or the signature of the function. We are going to have a directory to consume, a number to produce. And it computes number of, let's say, characters, or if we assume that characters are single, one letter long, or one character, one single string. So this is the thing. So now let's consider some examples, or maybe with the test cases. So we do have, let's say, function name. Let's say, how to say it, like the name of chars, and we consume a directory. So what is the template of this function? This is the header of the function. But what's the template of this function? Can someone tell me what's the template of this function is? A template of which one? This template should be, ready to go template that we need to use. That means, well, I need to just take this template and implement this template. But the thing is, before implementation, now let's finish up the test case. So that means now let's give, since we have started to write a check expect case, Now let's do a proper input, which is let's say if it is D. Okay, if it's a D, what should be the output? It's 0. Can you give something else where we do have something to go? B? Yeah, let's go with B. But we need to check. B has F3 and F4, and F3 is this one. I'm not sure. So how would you compute this thing? The length of the characters? Yeah, it should be count. We should be able to count the things. So do you know there's a called string length, I guess? So that should have, yeah, 29. Don't forget that one. Now let's check this one. But you know, writing the examples hints us the actual implementation, what we need to do during the implementation. It's always good to examine examples and do analysis. So in this case, we will have another text like this one, and we are going to somehow compute the thing. But we could actually compute. So what should be the output of this thing? If it's B? 29, is it 29 plus? Yeah. So that's a simple case. So now focus on the design of this function, implementation of this function. Definitely we now have a different function, which is chars is the name of the function. Now let's see what we have. Are we going to use the directory name information? No. So we don't need to use it at all. So we will get rid of it. See? When you go from template to design, you get rid of the things, not on the other way around. Okay? But now we need to design a function which computes the number of characters within the files or instantly under the current directory or within the subdirectory. So we need another function. Let's say subchars. I don't know. I didn't come up with a more proper name. So this is it looks like we are done. You know, in design wise, now we need to go and design this function. Subchars. And what is the
There's an error. So
yeah, what's it? Okay, we'll correct it.
Files in the directory and direct files in subdirectory. So we should make or implement subchars with two inputs. So we can compute the actual directory and go to the subdirectory.
Yeah. That's what I have done is just follow the data definition. If we do follow, we will come to that point immediately. Because we know that this is a list of files and directories. We have came up with this template which extracts files and directories separately. So we'll take care of the things within this implementation. So that's the idea of using this reflecting data definition to organization.
In this case, it will be just D, not D slots. So we're producing the.
Now, at this case, what we extracted is a list of files and directories, and because now we can use the template of this function. So within the list of files and directories, some of them will be files, some of them will be subdirectories. So we will consider them separately. That's what's your point indeed. But we have done with straight implementation. We are following your point, but just following straight implementation because following the design principle, design recipe principle. That's actually mechanical but beauty of design recipe. You might not come up with that idea in first place if you don't follow the design recipe. But if you do follow the design recipe, it leads you to this idea. That's the point of following design recipe indeed. So let's come back to here. We consume list of files and directories in this case, and we are going to produce number. And what template are we going to use? Obviously this template. This is the reason we had this template in the first place. We are going to implement the template. So, but we are going to make changes in first place, at least for the names of things we are going to. It's called subcharts. Yeah. Subcharts here. We do have self-recursion here for the subcharts, and we do have another self-recursion here. So now let's examine the other components. In this component, did we design anything which works on the file itself? Do you think we need? So now we can focus on the purpose of the function. We do have whatever we need to have. For this case, now we have the file, the current file, and we have answer for the rest of the files or directories. So that tells you I'm going to find answer for the rest of the directory, number of characters in the rest of files and directories, but this is the file you need to consider. So that means, well, actually, that tells you don't need a separate function in this case, because in an example we realized that we can use string length, because we know that the structure of the file is a string. If we extract actually the content, so that means first we need to extract the content of the file and then use this built-in function. How are we going to extract the content of the file? We know that this is file and the content is the selector operation. So now we have content of the file ready to go, and we can use this built-in string length. Sorry. I was following Kemal's suggestion. So it's a string length. So now we have a number out of string length, and we do have a number from the thing, and we want to sum them up. So it's simply a summation. So where did I? Yeah, it's a simple summation where we do have the things summed up. So now that will help us. It doesn't differentiate actually what's the rest of the files or what is the rest of the list actually. It might be a file. If it's a file, it will get back to that point. If the directory will go to down here. But let's do the case for the empty situation. It's 0. Okay, how about this one? Now we have the first item is directory. So that means we should be able to a subdirectory, that is. That means in this case we should be able to come up to extract all number of characters in the subdirectory. Is that something familiar? Is that reminds you something? It is the main function we want to design. The function is given a directory, find all characters under that's the directory. So that means actually we have designed this function. Yeah, sure.
Why we're writing first locked instead of just locked?
Okay, this is list of files and directories. It's a whole const structure. What we have done is we didn't decide it here. We decided.
Before this one, after first. I mean, after file and question mark, we are writing first locked.
Actually, we mentioned this before because lofty is what? Is a const structure. Actually, we dealt with this again in the template. That's what the point, the place, the exact address where you want to deal. Because we remember from the design of the list of files and directories, we know that it's either empty or a const structure. But the const structure will have two dual shape, where the first item might be a list, a file, or it might be a directory. So what you need to check here is whether the first item is file or not. That's why you need to ask this question. If you haven't written this question, that will be a wrong thing, because it will produce a false all the time. Because we know that's lofty's const. So every time you will have a false answer in this case. That's the reason we have extracted the first item. Okay, now let's come back to the rest of the implementation. And we were considering what we need to do, and we realized that the first item is a directory itself. it's again the same function we want to design, and we have designed it up here. I completed the implementation. So that means now I'm going to use chars to do so. So now let's look at the things again. I have the first subdirectory that tells me that I'm going to find out every length of the characters under the subdirectory for everything underneath. And this tells that it's going to take care of the rest of the list. What are we left to do? Is just what? Sum them up. So this is really simple in a way, and that reminds us what was the contract of this function, rewrite it. So I want you to examine the implementation again. So this is a mutually recursive function. We have two separate functions. They collaborate. How they collaborate is determined by the data definitions we had. So you start with our directory, and you go back to the list of files and directories. It checks if it's filed, it comes up with the answer with that single file in @zop. If it's a directory, it sends back. So that's how mutually you sum up, you collect the information you need to do. That's mutually recursive function. And the thing is what we have done here, we do have a function like the first one. That first one, this is chars. It leads us to go, it extracts, but what it does is extract its subdirectories and files and passes this to the other function. Subchars or chars sub. Yeah, subchars. So what we have done here, once we extract, we come back to here. In this case, there are two cases. Every one of them, either they go back or to this one. In the first case, they go back to itself. In the directory case, when the first item is directory, it goes all the way back to the first function. So now it's hard to say which one is auxiliary or which one is the main function. You have an answer for a problem where you are given list of files and directories. You want to collect length of characters under that list. So you might start with that one, but interactively you go from one to the other. That's a simple case you would come out with. So now let's check if really it works and then fix any problems if we have. Well, we don't have any problems, but let's start with some cases manually, see if it's A, for instance. It finds all the things underneath. So this is a simple yet very nice and neat design because it's based on design recipe. This is actually a very good summary of structural recursion. In structural recursion, the whole idea is you reflect data structure to your design. So it's a primary thing you need to do. And next semester we are going to move on generative recursion. In generative recursion, within the design of generative recursion, we will use structural recursion most of the time. But our approach to generative recursion will be slightly different. We will be able to use invent algorithms and implement the algorithms. So structural recursion is actually a subcomponent, or actually subset, as a design approach, is a subset for the generative recursion. But the beauty about structural recursion is, if you're really familiar, get used to design recipe things, that means you will end up really cool designs without considering lots of algorithmic things by analyzing data. Okay, that's one thing I wanted to mention. Any questions for this one? Yeah.
Yes, maybe as a question, but can we implement these two functions
in
one function?
As a single function?
Yeah.
Yeah, you could implement them with a single function. Yeah, you could implement but it will be messy. And you would confuse the data definition, and also whenever you go back to the self-recursion, every time you need to extract things and so on. And the way you will deal with it, you have no outline of the thing. With the design recipe, you have an outline, and the outline is the outline of the data. That's the idea. That's why you could come up with a single function and do so. But in this case, you are using the same template. So for instance, you can come up with some other some other function you want to design. It's like list the names of the directories and files. So in this case, there might be cases where you might have more stuff to do in this part. By separating them, you are just making things look neat and work neatly. That's the idea of that kind of approach. Any other question? Now let's have a break and we'll keep doing some other stuff. So for the second part, we are going to examine two cases. In the first one, we will look at a function design where we consume a function and produce a function. So it's like higher level abstraction in a way. So for this, as an example, we will look at one thing from math, like we will do computational math in a way. So our purpose is, given a polynomial function, let's say is something like that, we want to produce its derivative function. So our purpose is, you give a polynomial function, and in the end you are going to return its derivative. So that's the thing we want to design. But in order to do so, we should find a way how to examine a current polynomial function and come up with its derivative. Any idea? In math, what would you do how would you find derivative of a function, let's say, at that point? So this is an x0 point, and this is fx0. How would you find the derivative of the function at that very point? What's the derivative of that function in that point?
You can go from the definition of derivative.
Yes. So yeah, it's a way we will use limits. But there's this very simple thing. So you know from math that the tangent line at that the slope of tangent line at that point is also the value of the derivative function in this function. So if you want to find the fx0, the derivative of the function at the fx0, so what would you do is like write down the slope of the function at the tangent at that point, and assume, now I'm exaggerating, pick another point which is x0 plus epsilon. Maybe this is the epsilon distance. Why I'm saying epsilon? Because it's like very small distance, and you will take this, then this is the angle. Actually now you have to, so the difference from here to here is epsilon, and now if the line, the tangent line, or the slope of line at this one is, if it's a is over a, that's why it's called tangent line. And we know b is epsilon. And what's a in this case? How would you compute a, which is the distance here? So that is also tells you that is f x0 plus epsilon. So that means, how would you compute b? The a, sorry, in that case. So it's the fx0 plus epsilon minus fx0. So that will tell you how you could come up with the slope of this function, which is fx0 plus epsilon minus fx0 is divided by epsilon would give you the slope. So this is a single observation based on a single point. But if you want to, this is like a numerical approximation actually. Why is approximation? Because the larger you get the epsilon, the error you make will be larger. So what we do is like a numerical implementation of taking derivative of a function. So we want to implement numerically, which means computationally or programmatically, to come up with a function which will be derivative function of a given polynomial. So you can, from this one, you can generalize, say that the derivative f prime is f prime x is fx plus epsilon minus fx divided by epsilon. That gives you a function. So we will use this transformation, this numerical transformation, implement this numerical transformation in our design. So that's one approach we can do to come up with a function. We are going to implement a function which consumes a polynomial function and which produces another function which is derivative function of the thing, but numerically. So that means it's not exactly, it won't be exactly correct. So now let's design this function. So can you tell me the contract, this is sort of higher order functions you would do. So what's the contract of this? So it's the f prime is the name of the function. So find the derivative, or actually not f prime. Take, I'll say, derivative. That will be a proper name compared to f prime, because f prime is what we produce indeed. We will consume f, we will produce f prime. So that's an operator. So it will, sorry, come on.
It will consume a function f and an epsilon.
Yeah, a function f and epsilon. Maybe we can implement epsilon separately as a constant, maybe like a global constant. So then you can play, or actually you can parameterize it. Let's say parameterize it, epsilon. So based on precision, you can directly implement this thing.
Can we choose epsilon and like arbitrary change function, maybe something?
Yeah, you can come up with, that will help you to come up more precise numerical implementation based on the structure or fluctuation in the function. For instance, if it's a smooth function, epsilon 2 will be enough even to find derivative. But it's a varying function, you might need to have smaller distances. So you can come up with more, in numerical implementation, they do care such kind of things. But now let's decide we implement epsilon within the function just for another purpose, not because of the design purpose. And we will see that. We are going to produce an f prime, but this is not the contract we would have. It's not a proper contract. That means this is an operator you are going to consume, and this is an operator you are going to produce. How are we going to reflect the contract in a proper way? So what kind of functions you should tell what kind of functions you are going to consume and what sort of function you are going to produce. So the function we consume are polynomial functions, which works on numbers. That means we should tell the contract of this function. So for this thing, we will consume number and we'll produce a number. That means we produce another function, but the function we consume itself is a function. So now, differently, we should tell that the output of this thing is again another function. Is again the same sort of, because the derivative of a polynomial function is again a polynomial function. And we know how it works. So we do have this contract. Now, I'm skipping the purpose. Now let's do the implementation straight ahead. So to make time. But so what's the contract of this function? What's the contract of this function now? This is the header. What should be the contract of this function? So we have input f. We need to extract data we want to use. But this time the data that we consume is itself a higher order data. It's a function. So we will have just maybe f here. We need to actually use function within the body. So that would be just straight, simple template. That's why we have nothing much to do. Now what we have to do is somehow we should be able to reflect this implementation within the body of the function. One additional thing I want to mention today is an if construct, because now I want to first of all define the epsilon like within the body of the function. For instance, the epsilon for current, like that's 0.1. So that means my definition of epsilon, I want to use epsilon encapsulated within this area. But now I also want to somehow use this derivative function, which is, let's say, define which is f prime, what I'm going to produce. I want to produce this f prime. So it's f prime, and f prime consumes, a function g, let's call it, or maybe just, f prime, let that function g, and it's going to produce, let's say again, f, and it should produce the thing. Or instead, I can just implement f prime because I'm going to use the input f immediately. I don't need to re-parameterize it in this case. F prime will be an expression. What's the expression for this one? It's that expression we had. And that expression tells us that what you need to do is divide the difference between, for A, by B. B in this case is epsilon. So this is the main expression. Now I have to find out what's the expression here. Is f. Oh, that tells me that f prime should be a function, and that's the thing I'm going to produce. And that means I need to reflect this contract here within the function, because the thing I'm going to produce should be able to consume an input x later on. That's why f prime here is, I need to be clear about the contract of the f prime. So that's why I have it here. And then based on this contract, I realized that I need to consume an x later on to work on it. So now this is, the x is not given in this case. We have just given the function. But the function I'm going to produce will be ready to consume another input. That's how the contract says. Okay, so that's why we parameterize the input. But the parameterized input is not the function, but the input is going to consume later on. The numbers is going to consume later on. That's how we realize that we should be careful about this. And now we are going to compute fx maybe plus epsilon. This is this expression, and minus fx. So we have the nominator full, so this is a over b. That will be the full expression. So what do I have done here? I have defined a function, a separate function, but in this function definition, I say I'm expecting an x to implement, to apply this function. And also I have determined the epsilon. So these things are, I actually limited availability of this function within the body of another function. Syntax-wise, you can do this in Rocket, but the way you can do is use a local expression. So that means you localize some definitions. So the local expression is like, it has two components. The first component, you separate a space where you have your definitions as the one input area, where you make your own definitions, and as an expression area where you use the things you have defined. You can use the things that you have defined along with the inputs, the main inputs. So the simple syntax is, now we have, that means I need to put things in between parentheses for the definitions you had. So for instance, this is the first definition. I think it's not complete. Yeah, this is the first definition, or maybe to make it more clear, this is our first definition, and this is another function definition we did have. So now we have, this is the first component of local. Then you should be able to use the things coming from the input, and also the things you have defined within local area. So in a way, having this local syntax, like you open up a definition window within the body of the function, an interaction within the body of the function. So this somehow restricts the use of definitions just within the body of the function. This is the difference. If you want to hide some function implementation to be used by other functions, you can use them within the body. So you limit the scope of the availability of the functions you have. So now, that means in this case, what would you return? This f is the input f. So the scope of input is available whole area within definition area. So now we know that this f refers to input. So this is the function we have consumed in first place, and what we want to return is actually this function itself. No implementation, but just this function. So that leads us just to return the f prime. So this is the local, and it will give the whole implementation. Any questions so far? We are going to check this, actually, how it works. Let's check if there's anything wrong. And if I tell, for instance, derive, that will say nothing because it's just a function. But if I implement derive with a, for instance, square is an operator. Let's see how it returns what? I have passed a function which takes square is like x squared. Whatever x is taking x squared. And what should that produce in mathematically? What's the derivative of square? What's the derivative of square? It's 2x. So that means it has produced a function, something like lambda a1, which the body of the function will be 2 times a1. This is the thing it should have produced, which if it was proper, not numerical, but proper definition. But what we have produced is like we have somehow produced a numerical value which might be closer. So but the thing is, what we have in the end is a function. We have returned a function, and you can see that as well here. So in order to use this function, so that means this is what you have here is a function. How would you use a function? You will apply it for some input. Now if you say 2, what should we expect for ideal case? 4. It's 4.01 because we have an epsilon error margin. If you, for instance, let's say decrease the error, you might have like increase the epsilon stuff. So now let's try it again and see so you decrease the error as well. So the smaller epsilon you have, the better numerical value you get in the end. But for instance, you can use instead, for the derivative, instead of square, you can pass on some other functions like lambda x. For instance, square of, it's a polynomial, so I will sum components up. Let's say something more like square of or cube of x, anyway, square of x times 2 times x, for instance, and let's say and 4. This is simple, like x squared plus 2x plus 4. It's x plus 2's function. So how about what should be the output in this case? So this is the function this is the function, complete function. Now this function is the input for the derivative. Let's check this first. So again, it produces a derivative function. How about its value at 1? It's 2x plus 2. 2 is, come on guys. We have input is 1. It's 2x plus 2. It's 4 because 2x plus 2. Okay, how about 2? No, it's 6. Okay, so that's an example case. We will use such kind of function which produces functions more dynamically in second semester. But it should help you to understand the syntax. So now I'm going to move on our last example where I want to cover today. In this case, we will look at a very general problem that we might use in several different cases, and maybe basically like in merge sort algorithm. So the thing is, you have 2 lists of inputs, like 1, 2, 3, 5, 6. Another like 2, 5, 7. What you want to get in there, because as you have realized, we have a input list 1 and input list 2, they are all in sorted manner. So they are all sorted. So what we want to make is like merge them and produce 1, 2, 2, 3, 5, 5, 7. Okay? So we have two lists which are sorted within themselves separately, but we want to merge them. The interesting thing about such kind of problem is we want to apply structural recursion design to complete the implementation. And as you have realized so far in structural recursion design, if there are multiple inputs, we examine which input is active input, which means which input determines the actions, the expressions, that the way we traverse throughout the implementation. And we construct the template based on this active input. So, but this case, we have two inputs. We might need to go on these two inputs in parallel. So that means you should come up with a general approach for the implementation of functions, apply design recipe to implementation of function where you have two or more active inputs at the same time. So that's the case we want to cover by this example. So now let's start with. No, before let's starting, what will be your approach? I mean, definitely we are going to use list of numbers. We don't need to come up with a new definition. We have done it this before. So the thing is, now we consume list of numbers which is sorted, and we are going to consume another list of numbers which is again sorted. So, and what are we going to produce? Another sorted list of numbers. So this is the thing. So our purpose is to merge them, keeping their order property. Or it's like so. What's the thing is what's the template of this function? Yes. So before giving some template, let's do some example cases. For instance, let's say we call it merge. Input 1 is empty, and input 2 is also empty. Or I can just simply write empty here. What should be the output? It should be empty. This is so simple case. How about, for instance, let's say we do have an empty case, the first input, and non-empty case like 2, 4, 6, 9. What should be the output? So the same thing, because and 9. This is one other case you might need to. How about some other extreme case will be what? You might have a non-empty first list, like 1, 4, and 9 again, an empty and second list. What should be output? The first list. Directly the first. You don't need to do anything else, just return the first list. But a non-trivial case, all of the cases are sort of trivial cases. In a non-trivial case, you will have, let's say, merge 1, 2, 5. Another one is 2, 3, 6. What should be the output? 1, 2, 2, 3, 5, 6. So I think we have covered almost all cases. And that should help us also how we need to organize our templates. So now think about the templates while I'm writing the header part. So we have merge, we have list 1 and list 2. So
We should cover the trivial cases first.
we have
We should cover the
trivial cases.
It's empty and empty. The first is empty.
Sorry.
Return the second list.
So what we have done is actually, if you look at we covered good examples which covers all cases. where the first, if it was just a single primary input, we would have two cases, and this would be whether the list is empty or non-empty. But in this case, we have two other options. So we have a 2 by 2 by 2 different scenario, and as a general rule, this is a trivial case, but you can apply the same rule to any complex sort of inputs. And you have L1 and you have L2. You know that L1 can be empty and a const structure. You know that L2 can be an empty and another const structure. So that's the thing. You will come up with the proper question cases. So that leaves you that you have to ask 4 different questions to determine which one is the case. So that means we will have 4 branches in our conditional statements. So that's the idea. That means you consider the definition of both inputs at the same time if you are going to use them in parallel. So that was the example I wanted to highlight. So we have both empty case, the first empty, the second empty, both non-empty case. So now we have to formulate the question and empty the first one and empty the second one. And we will take care of it later on. So now how about the question for the second case? First input is empty, and second input is, let's say, just do straight questions. We might improve our statements later on. The second one is a const case. So this is the question. And how about the other thing? We will have just other way around the question. So we will have const, the first one is the const structure, it's a pair. The second one is an empty. So we do have this thing again. Now, how about this case? Where both of them are called, so it's an else case. So now let's keep working on, so if both of, so this is the questions we have formulated. This is the first stage when you have multiple type of inputs, like if the input might be different types, and you might, or values based on if it's an itemization. Now the second stage is to examine if you have to open up things, and if you have open up things where you need to have a recursion, self-recursion or cross-recursion. If both of them are empty, there's nothing to do with, but if in this case list 1 is empty, that means we need to consider list 2, and list 2 will have a component, first component, and a second component. How about this one? This case, we will list 1 is non-empty, so that means we need to extract the components of list 1. And this case, actually both of them can be non-empty. Indeed, both of them are non-empty, so we need to extract all components properly. So this is for list 1, and the second line is list 2. So now we have done the extraction, but now we need to check in which cases we might need to do recursion. If you check our self-recursion, to go for the self-recursion, we need to have 2 lists. In the second case, there is the item number, but there is the single list, so that means this is not the candidate for a recursion. But somehow, for this case, we might use to have list processing function if it's necessary. If you have realized I have forgotten about the purpose of the function, I'm focusing on how would you reflect the template when you have more than 2 complex inputs. So I have focused on how we organize the things here. So now for this case again, it looks like that there isn't any proper candidate for a self-recursion because we will have a single list. But let's check this one. Obviously there are 2 lists that we might need to use. So that will hint us we are going to do recursion here. but not sure how are we going to do the recursion. Maybe the first one and the second one we are going to use at the same time, maybe, or otherwise round. But the thing is, if you just follow principle of design and implement it in a template, that will the template you will end up with. So now let's keep it to make comparison with the implementation we'll have later on. So I'm just going to keep it to make the comparisons. So now from that point on, let's focus on the full implementation. If both are empty, so we do have this empty thing. So if the first one is empty, the second one is not empty, what are you going to do? Return the second one. You don't need to extract and repack. So extracting and repacking will be really redundant work. So to decrease the redundancy, you would just use the second one. The same thing goes for the third case as well. So this is this one. How about this case? It's not so straight. What would you do, just based on the examples we had? We should compare the first items. So, and based on the first items, we will keep moving on. That means we need to do comparison based on the first item, the first of the first list and first of the second list. So we will do the simple comparison whether, for instance, this one is equal or smaller than the first item on the second list. So if it's true, what would you do? You realize that the first item and the first list is smaller or equal to the second one. What would you do? Hold the first one. So we were going to take the first item. We keep the first item. I mean, take this into new set. Put them into a new list. So we will keep the first item. So what are you going to do? So now you have the first item, and that's the point where you go for the recursion, isn't it? So that's the point where you decide you are going to do the recursion. But you should be careful about how recursion is going to be implemented. So are you going to keep take the rest of the first item? Because you extracted the first item, and you have to look at the rest of the first item, first list. So you keep this one. How about the second list? Keep it as it is, because you haven't extracted anything from the second things. So that's why you keep it as it is. So we will have the second one. Now what are you going to do? How are you going to combine them? By constant, by putting them into pairs. So that's how you would deal with for the first case. How about if it's larger? What would you do? In else case, what would you do? Yeah, we will do the same thing, but we will take the first item of the second one and recurse on the rest of the L2 and keep L1 as it is. So that's how you would proceed to complete the whole implementation. So that means that for this thing, we won't touch the first list, but sorry, I did the wrong place. So we will keep the first item of the second list, and we are not going to touch the first list, but take the rest of the second list, because it's where we have extracted the thing. So I think I have closed, now I have closed things and should be working. Let's try it manually, test it manually. We have tested it, actually. We have test cases up there, but let's test it again, make it manually. Like 1, 2, 8, and 2, 7, 9, 9. So it should produce the thing immediately. So that was a case where how you will approach to function design where you don't have one single primary input, but two or more primary inputs. But actually, we have given an example with two cases. If it was a third input, which is again non-complex, you would examine all different cases. But the thing is, you can work on separately and then look at the things and refine and maybe decrease number of conditions you have. Do you think we can decrease number of conditions we have here? So, for instance, we can maybe instead of decreasing number of conditions, how can you improve, define implementation here to make it, to get rid of redundant expressions? Because redundant expressions is cost, is a computational cost. What kind of, how would you improve it? Any idea?
Yeah, actually, okay, I got it. If there are no two parameters, if there are no two lists, you can just return the list as because there will be an empty list.
Yeah, but the contract says that we are going to have always two lists. Yeah, that's the contract of the function.
And list can be either empty or a list, so we can just return the list as is. If
Yeah,
there are no.
but for the, yeah, I know, but still, can you decrease number of branches here? Does it look that you can decrease number of branches? Like, that looks like this is candidate if we had a way to parameterize both lists at the same time. But since we have separate lists as inputs, we are not able to maybe merge them in that perspective. But what you can do is, if none of them empty, if not both of them empty, you don't need to ask whether L2 is empty or not. If L1 is empty, definitely, if you are in this case, L1 is empty, we know that L2 is not empty. If both of them were empty, you would use the first case. That means you can decrease the questions. One question is here. You don't have to ask this question. The other question is, you don't have to do this logical operator. Just ask whether list 1 is empty or not. And again, the same thing holds for this case. You don't need to ask this one and do the logical operator. Just ask whether the list 2 is empty. So that will decrease and simplify implementation and decrease the redundancy you have. So see if it works in that way. Yeah, it's fine. So that's all for today. But if you have any questions, I would like to take them.